Wow, there's a lot of you out there. Good morning, and welcome to my talk on the Adventurer's Guide to Forking the Go runtime. My keyboard's not working. There we go. My name is Dominic Black, and I'm a founding engineer at Encore. For those of you who don't know, Encore is a back-end development engine, and our passion is improving the developer experience at building scalable backends on the cloud. And this talk is based loosely on how we give you distributed tracing for free without you having to even think about it. So what's our goal today? We're going to create a fork of the Go runtime. We're going to learn more about how Go's internals work. We're going to add distributed tracing to an existing set of microservices. And we're going to learn how a small change to our tooling can massively improve our experience as developers. So the first question I think all of you are shouting at me is, why fork Go? Like, this is something that nobody should ever do. And my answer to you is, why not? We have a massive advantage of Go developers. As we learned this morning, Go is now written in Go. So if you know how to program anything in Go, you know how to modify the language itself and the runtime. And don't just take my word for it. All of these companies have their own version of Go. Microsoft maintains a FIPS-compliant version of Go for the use in the US government. Tailscale have a copy of Go where they've added extra security and safety in the networking code. Uber had 2 copies of Go, which I don't know if they use anymore, but one of them was, I've linked to this blog post here, was a really interesting deep dive into, they had a latency issue, and they had to basically start adding print statements in the lowest level of the runtime to understand what was happening, and they ran out on their production systems for a while. We have embedded Go for running on microcontrollers, and then we have Encore's version of Go, which, as I said, this talk is based on. So I've been lying up to now. I said we're going to fork Go, and that's not quite true. We're going to create a rolling set of patches that we can consistently apply to Go. So the way we're going to do this is we'll create a blank repository. We'll check out the Go release branch as a submodule. And Go's release branches are really lovely, because the latest commit on that release branch will always be the latest point release for that version of Go. Once we have that, we'll create a patches folder in our repository. The patches folder will contain the diffs of what we're actually changing within the Go code itself. And we want to keep these diffs as small as possible. The reason we want to keep them as diffs rather than just directly modifying Go is twofold. Firstly, when a new version of Go comes out, we want to be able to reapply our diffs. And if they don't apply cleanly, we want to be able to rewrite them easily. The second reason is at the top of diffs, it's very, very rarely used, but you can actually put like an entire text document if you want before the diff starts. So you can describe what the diff is doing, why you've made that change. And this means when somebody comes to audit your code, they can just read the description of what the diff file is trying to do, look at the diff and understand, OK, cool, that small bit of code does what it says it's trying to do. And they don't have to worry that you've modified the language in some other way that they need to worry about. Lastly, we'll create an overlays folder. And this folder will contain brand new files that we intend to put inside Go itself. And the separation of patches and new files is, again, just to keep it cleaner and keep it easier to understand what we're changing. All new files in this overlays directory will be completely isolated from the existing code base, and so it's easy to understand what they're trying to do. And if we keep those patches as small as possible, it's easy to understand how we've integrated the new code to the existing code in Go. So once we have this repository set up, we need a quick build script which we can use. So this script here is based, again, loosely on how we do it at Encore. So we'll just cd into the directory where the Go submodule is. We'll do some git magic to check out that latest version of Go 120 in this example. And we'll make sure that we clean it and remove all our existing patches. Next, we'll apply our patches from that patches directory, and we'll apply a copy and any overlays. And then finally, we'll just cd into the source directory within Go and use the existing make.bash. At this point, if we ran this script, we would have an identical release of Go 120.7. But that's not what we're here to. We're here to make a copy of a modification to Go. So let's do that. Let's make our first patch. And as I said earlier, like, we can put a description at the top of this patch. So without even reading the code, you know what I'm trying to do here. I just want to change the version of Go from Go 127 to forked Go 120.7. And all we have to do is change 2 lines of code in the distribution build system to achieve this goal. So that's what this patch does. Now, if we run our build script, we can then run Go version on the built version of Go, and we can see that now it's reporting it's forked, and it's not Go, it's Argo. So now we have a custom version of Go. So let's start making a bigger change. And I'm going to start making this by talking about what is actually a Go routine, like what's happening under the hood. So I've got a very simple application on screen now. It prints main called, it then starts a Go routine, prints Go routine started, and then prints main finished. You run that, you get what you expect. But what if we were to add a print statement every time a Go routine starts, every time a Go routine stops, and when the actual program starts and stops? To do this, we actually need to understand something about how Go works internally. So if I said to you, what's the entry point for a Go program, I think most of you would say it's main.main, it's the function you've written. That's not true. There's some assembly code which starts initially, but then it actually hands over to a main function in the runtime package. And the main function in the runtime's package starts initializing all the package level variables or your init functions. Its job is to start up Go. And once it's done that, it hands over to your main function. So this is really an interesting sort of sidebar here on how init functions and how package level variable initialization works in Go. As Go programmers, we normally think, all of that happens before any of our code can run inside a package. And in the runtime, that's not true, because something has to call that code, and that's what this runtime main function does. So when the compiler comes along and it sees your init functions, or it sees package level initializations, variables being initialized, it basically creates a list of all of these tasks which need to be performed for your package and what packages your package depends on. And then the main.main function, the runtime.main function basically goes through these tasks, executing them one by one, and then hands over to you. The other thing that I think we need to understand is how Go routines are actually modeled. And there's 3 struts within the runtime package: the G strut, which stands for Go routine, the M strut, which stands for machine, and really this is just a operating system level thread, but the name machine kind of comes from the Plan 9 lineage of how Go was originally built by the team. And then the last strut is the P strut, which is a processor. And this represents like the actual thing which is running Go code. And there's a really awesome design doc I've linked at the bottom of the slides here, which talks about how the scheduler works. So let's start adding these print statements I talked about. So I've got a patch here which modifies the runtime.main function and just adds a print statement at the beginning and a print statement just before the system exit call. And then we then modify this weird function called goExit0, which I guess if you read the print statement, you can see what it does. This is a function that always runs whenever any Go routine exits, and it runs on the system stack. So we know, OK, this Go routine is now stopped. It's not running anymore. And lastly, we have the equivalent, but in reverse, new PROC.GO, which runs on the system stack whenever a Go routine is starting up. So now we've added these print line statements to our program, we can rerun our program. And if I asked you what the output was now, you probably wouldn't say that. And this is like another interesting sidebar here. So we have the main Go routine starting up for the entire program. That makes sense. We then have the runtime's main function starting, and that's what we expected. But then we have these 4 other Go routines. And these are all stuff that the runtime is starting up before your code ever gets called. So these are like the garbage collector, the finalizer system, and a whole bunch of other things going on here. Eventually, we see our main function get called. We can see our Go routine starting, and we can see our print statement from that. We can see our Go routine exits. Then we can see our main function exits before Go's runtime's main function exits. Now we've made a small change, we can start thinking about how we might use this for tracing. So as I said at the beginning of this talk, we're going to modify a simple set of microservices. And this is the simplest thing I could think of. It's an API gateway, which when it gets a request, will talk to a user service and ask to authenticate a user. And then once the user's been authenticated, it will talk to a to-do service to let the user interact with their to-dos. So I'm going to have a quick look at this code. OK. So this is the main function for the API gateway. All it does is listen on port 8080, register a bunch of routes, and then inside those routes, for instance, list to-dos. It calls an authenticate user call, which calls off to the user microservice, and then calls the to-do microservice to list the to-dos. I've built like a very small like REST library here to abstract away all the marshalling and networking for us. But under the hood, if we have a look at it, you can see all it's using is the inbuilt net HTTP server, some Zerolog, because I'd built this before slog was in the standard library, and that's about it. So if we run this microservice now, we can see that we have 3 microservices listing on different ports. And if that's not what I want to do. And if I call the services, I get my to-do back. If we go back to the output from those microservices, we can see like just a log statement saying, oh, I'm handling these requests for these URLs. We can see the API gateway received my request. We can see the user service received a check auth request. And we can see the to-do service received a request to get the to-dos for user 1. So what are we going to do now? Well, let's think about how we want to do tracing. We want to modify Go routines to carry trace identifiers for us. We want to modify the inbuilt HTTP server and clients to add start traces for us and add spans for us automatically. We want to modify the SQLite package in the standard library to automatically add spans for us on queries. And then we want to push all of this information to Jaeger. So let's start with the Go routines. And we want to start by thinking about what do we actually want to know? What do we want to know when it happens? And there are 4 things I think we need to be able to do with Go routines here. We want to be able to attach tracing data to a Go routine and say, hey, this Go routine now holds this data for us. We want to be able to get that data back. We want to then be able to know when a Go routine that is carrying trace data for us spawns a new Go routine. And we want to know when a Go routine which is carrying trace data exits. So on the right here, I have 4 function prototypes where you notice there's no bodies to these. And these 4 function prototypes basically implement what we want to know and what we want to be able to do. And you'll notice that we've put this in our overlays folder, so it just gets copied into the runtime for us. Then we want to patch the gstrut and add our trace data directly into the gstrut. And then we can implement the body on the attach and read functions by calling getG, which always returns the current Go routine's gstrut, and just read the variable and write the variable. Finally, you'll see here, I've added just a simple helping function to get the Go routine ID, and you'll see why we use this later. Then we can modify Go exit 0, and instead of printing this time, we just do the simple check. If there's trace data, call our hook for us. And with the new PROC.GO, we do the same thing. We're like, if there's trace data on the calling Go routines strut, then let's set on the new Go routines strut the trace data return from our tracing start function callback. Now, this is where we get to some interesting stuff, I think. So we're going to create a tracing package outside of the Go source code. And the reason we're going to do this is almost everything in Go relies on the runtime, directly or indirectly. And we have this annoying thing called circular dependencies. So if we want to push data to Jaeger, that's going to need to push data to the networking code, which in turn will call the runtime code. And if we're inside the runtime while we're trying to do this, we're going to have a circular dependency. We can break this dependency by being very, very careful and putting all of this code outside the runtime and then using unsafe to allow us to do some really weird stuff. So there's a directive that most people don't know about in Go called Go link name. And this allows us to tell the linker after the compile step, hey, this symbol here and this symbol over here, they're the same thing, link them together. So those function prototypes that we saw a couple of slides ago, we're never going to write a body for some of them because we're just going to tell the linker the body's in this package instead. And the linker is going to quite happily allow us to compile that. And this means that this package can import the runtime as you see, but there's no circular dependency between the runtime and this package, even though the 2 packages are directly calling each other. Also note how all of these functions are completely unexported. There's no like public APIs we're making here. We are simply just using the linker to allow us to directly access stuff that otherwise we wouldn't be able to access. You'll also see here that I've changed the data type from an unsafe pointer to a pointer of this new Go routines trace data strut. And that's completely fine because once the compilation is completed and we're just linking all these units together, we're just dealing with pointers anyway. So there's no issue there. And now between the runtime and tracing package, we have implementations for all those hooks we just looked at. And we can start thinking about what we're going to do. So as I said, let's think about the HTTP package. And just like we did with GoToRoutines, let's start by thinking about what do we want to know, when do we want to know it? Well, we want to know when a server starts handling a request, when it finishes handling a request. We want to know when an HTTP call is about to be made and when an HTTP call has finished. And we'll also need to add a tracing.s file. And this is kind of going to catch you out if you ever try and use link name and you haven't done this. So an S file in Go basically says there's some assembly code here in this package. And if you don't have any assembly code in a package, link name won't work. The link is like, why are you trying to do this? So by putting a completely empty S file in there, we've effectively tricked the linker into allowing us to use link name. Maybe we shouldn't do that, but this is the only way it works right now. So once we've written our hooks, we can start implementing them inside our tracing package within our app. So we implement handler start and handler end, and what we've done here is we've created a new trace data struct, and we've just used the GoRoutine ID as the trace ID right now. And that, again, we just link name from the runtime package. We attach it to the GoRoutine, and then we just print, hey, this GoRoutine started processing this request. And then when the handler ends, we just print, cool, the GoRoutine's done. And then really importantly, we then remove the data from the GoRoutine struct. And the reason we do this is we want the trace to start and stop with the request. We don't want that GoRoutine, if it goes away and does something else in the HTTP server, we don't want to see that appearing in our trace because that's unrelated to the activity we're interested in. We also can implement our round trip functions to say, hey, we're about to make an HTTP request to this URL, and hey, we finished the HTTP request, and this was the response status we got. Once we have those functions, we can then wire the hooks into the standard library, just like we did for GoRoutines. So what I should see here on the top left is on the HTTP server, well, the HTTP 1 implementation of the server, we just add a call to a handler start and add a call to a handler end. I've not shown the HTTP 2 server or panic handling, but you can imagine it looks pretty much the same thing. And then in the round trip struct, or in the transport struct, we've added the same thing to the round trip function, where when that starts, we'll log the fact that it's starting, and then we'll use the first statement to pick up the response data and give that back to our hook. So if we give this a try now, we should see, hopefully, some really nice changes. And it's true, you can't type when you're on stage. Let's do that again. So there's no change to the output. We haven't changed the program, we've just changed the Go library, the Go standard runtime. And you can see here now, when I made the request, GoRoutine 25 in the API service started processing the request, and then it called our checkoff endpoint. You can see then GoRoutine 38 in the user service started processing that request, finished processing that request, and back in the API service, we can see that we got 200 OK, and then it went on to call the to-do service. This is great, right? We've got some form of tracing now without us having to do anything to the application. The language is now doing this for us. But this isn't distributed tracing yet. There's no link between these two things. So let's fix that. So how do we relate them together? Each request should start its own action, its own span, but it should have a reference to what called it, what caused it to occur. Given we're using REST here, it makes natural sense to use HTTP's headers. And as Konstantin mentioned in the previous talk, there is a standard called the trace context. And specifically, the header we care about is called TRACEPARENT. So what is the trace context? Well, it's 3 bits of information. It's 16 bytes worth of a trace ID, and this is randomly set at the beginning of the request, but we don't change it once we've done that, so throughout the entire chain of actions, it stays the same. There's then an 8-bit random span ID, and that changes every time we want to record a new span, and there's 1 bit's worth of flags that we're going to ignore today because they're not that important. When this goes onto the header, it gets hex encoded, and then when we can just pass the hex encoding to recreate the struct. We can then modify our existing handler start function to try and pass the trace parent in, and we'll use that as the basis for our new spans. And then when in our round trip function that we had before, we can now modify that. So instead of printing, oh, this GoRoutine's about to do something, we can modify the HTTP request and add the trace parent before any request actually leaves our server. And at this point, we actually have distributed tracing. We have consistent tracing throughout all of our different processes. We just don't have a UI yet. So let's design a very simple span API. Like, we want to be able to start a span and end a span. That's all we care about. Within the Go routine, we want to treat them as stacks. And the reason for this is you can imagine that your server receives a request and then starts querying your database or does some other actions, and you want these spans to stack on top of each other. And then once you've got this idea of this spanning stack, then we also need to support the concept that actually the parent to the span might not be the current Go routine. It might be something on a completely different process. So you can see here the start span function takes in a pointer to a remote parent. If that's nil, then cool, the Go routine written is the current parent. And if that's not nil, then whatever that is our parent span. I've removed the actual implementation here, but it's all available on GitHub. So if you would want to have a look at it, please do. Once we have the start and end span, then we'll use the open tracing or open telemetry APIs, that's a typo, sorry, the open telemetry APIs to report it to Jaeger. And again, it's outside of scope for today, so please go have a look at GitHub if you're interested. But Konstantin's talk was great on that. So let's start recording spans. In our handler start function, all we've got to do now is call start span. And in our handler end function, we just call end span before we clear that Go routine data. In our round trip function, we can start the span to say we're about to call something, and then we can set the header. And it's very important to do it that way round because you want the outgoing trace parent to be the call span, not the parent span to that. And then when we end the round trip, well, we can just end the span. It's really quite easy. And we can go kind of even more insane. Go has a really good HTTP trace package built into it, which gives you like insights into the actual connection information as it happens. So we can modify our round trip start function to automatically just add this to every outbound request. We could then add a record event function so we can capture that additional information onto the span so we know like when the DNS resolution started and ended. And then we can just add that to every request. So once we've done that, let's talk about databases. And so the same thing again, like start with what we want to know. We want to know when a query starts, when it ends, did it error? So that's what we've done on the left. We've added these hooks. And on the right, well, it's incredibly simple now. We can just start a span, and then we can end the span. We then have to patch our hooks in. And there's only two places we need to patch them. Query DC in the DB strut. This is the lowest level point in the standard library that a query goes before it gets handed off to a driver-specific implementation. And then execute DC, same thing, but for like execute commands. And so at this point, if you're using the standard libraries SQL for anything, it doesn't matter because we're going to get tracing for that now. So we're done. And let's have a look at this code now. If I remember the branch name is, what did I call it? Oh, yeah. That's not what I wanted. So our output now doesn't have like these print statements. But if we go into Jaeger and ask Jaeger for traces, we've now got spans. And in these spans, we can see that the handler started. We can see that it called the check-off endpoint. We can see the various actions coming from, if I hover over here, you can see the various actions that were occurring thanks to that HTTP trace library. And then you can see the user service started processing the request. But there's something interesting here. What is this massive time gap? Like our API service says it took 3.5 milliseconds to make that check-off call. But our user service says it only took 0.3 milliseconds to do that. These are on the same computer. What's going on? We can actually add even more telemetry to find that. So we can go kind of insane. We could say every new Go routine being spawned inside our trace automatically gets a span. So we're going to modify our hooks here and add the program counter for the entry point for every Go routine as the first parameter to the hook. We can then modify our Go routine start and end functions to be a bit more clever now. They can say, hey, we're starting a new Go routine, and we want to start recording a span on that other Go routine. And by the way, here's the name of the function that was called as the entry point. So if we do this, then we get a very cool outcome, or at least in my opinion, you may disagree. I've totally forgotten the name of this branch. So now if we call this and ask Jaeger to search for all our spans, traces, we now have a new trace. And you'll see instead of 6 spans, we have 27. And all of a sudden, we have a lot of visibility into what's happening inside our application. We can see, basically, this is the IPv6 attempt. This is the IPv4 attempt to connect. We can see DLS resolution happening. And if we go look at the database code, we can see the same thing happening in the database driver before our queries are made. And you can even see the Postgres driver doing some stuff in the background there too. And this is really powerful because we've not had to change that application. Imagine we had 1,000 microservices or 2,000 microservices. Adding spans to every one of those would be a pain in the ass. But if we change the tooling we're using, now we just get it for free. But we can do other stuff by modifying Go. We could automatically capture all those logs and include them in the trace data. So you could do this by modifying the new slog library, the standard log library, or even just modifying the standard out pointer so that everything which is leaving via standard out on a particular Go routine automatically gets tagged and associated with that span. We could do stuff like modify the net listener or modify the TCP library so that if you're not using HTTP, but you're using something else like Caddy, which has its own implementation, or we can actually still capture all of that because we can modify the very base networking code in Go and say, cool, if a new request comes in on the TCP listener, start a request. When it ends a request. If we make a TCP connection somewhere inside that span, let's record it, let's include it. We could go to the extremes, and we can modify the compiler so that it automatically adds a span to every single function in our code base. Don't do that, because you'll end up with ridiculous amounts of spans, and if you're on GCP, that's going to cost you a fortune. But outside of tracing, we can do stuff by modifying Go's runtime that would be impossible before. So something we do in Encore is we monitor what unit test is running in every Go routine. So we can give you state isolation per unit test. And this means you can set all your unit tests to run in parallel and not worry about flaky tests because this test and that test are both trying to fight over the same global variable. We can do stuff like resource leak detection, where you can say, hey, you opened a file pointer, you opened a file in this request, but you never closed it before the request ended. Here's a warning, you might want to look into that. And we can even point to the line of code that occurred in. So I'd be amiss if I didn't say there are other ways you could do this. As we saw in the previous talk, you could manually add middleware and code to all your libraries that you use, and manually start adding starting and ending spans using the actual Go context to pass that trace context through. That works really well. We've done that in Go for ages. We've done that in other languages for ages. You just have to remember to do it. And if your favorite library you're trying to use doesn't support it, then you need to build an abstraction on top of it to add the spans yourself so all your developers in your teams can use your abstraction. Or you just go, you know what, we're not going to have spans for that thing because we can't add them without forking that thing as well. But if you modify the language, well, you can do that. The other thing we can do is we can use the cloud's native tracing ability. As Konstantin mentioned, GCP has an absolute awesome inbuilt capability that you have to do really little to actually start using. The other thing I think is really cool, which is coming soon, is the OpenTelemetry project is working on an eBPF-powered system, which is kind of like what we've done here, but instead of this being a fork of Go, which you have to compile your app with, they are injecting code at runtime into the various packages and adding those hooks. I think this is a really cool idea. The downside to this approach is it only works on Linux. It won't work on Mac or Windows. So I hope this has been inspiring and you're going to go away and we're going to have 1,000 forks of Go by the end of the week. But honestly, I think it's a really interesting idea that like the language itself is flexible and the language is powerful, but it doesn't have to be just that. Like if you need something extra, if you need to do something for your business, which would be a huge pain to do in your business logic, well, maybe it's actually really easy to do in the language, and running that modified version isn't that bad. Patching it isn't that bad. So yeah, that's my talk. And if everyone's got any questions, I'd love to take them.